This is a presentation of my final project to hopefully obtain a master's degree in data science from Regis University in Denver, Colorado. I am doing the Kaggle Earthquake Prediction Challenge. I chose this project because it can be approached as a regression problem, and I thought it was a good fit for my math background. Also, earthquake prediction is an important problem that could eventually save lives. Even though this challenge is about earthquakes, I do not have any geology background. Given the way the data is structured, I have been able to approach it as a regression problem using machine learning methods. As a bonus, though, years ago I took some extension signal processing courses through the University of California, Irvine, which helps a lot here, along with my machine learning and statistics at Regis. As an introduction to the project problem, it is a data science competition sponsored by Los Alamos National Laboratories and hosted by Kaggle. The earthquake predictions are not for real earthquakes, but rather for simulated quakes that occur in a laboratory setup. The prediction data is given as time to failure of the sample fault line, or this can be thought of as the time to the next earthquake. Failure, earthquake, and time to failure are essentially synonymous terms in this model for the same thing, a laboratory earthquake. The input data is an acoustic signal, essentially a sound signal, that contains 16 laboratory earthquakes. Each sample of the acoustic signal is accompanied by a corresponding time to the next quake. The problem becomes one of being given an acoustic signal that represents what is happening in the laboratory fault as it is stressed, and then trying to predict when the next quake will occur. For anyone not familiar with data science or regression modeling, training data is what we use to develop our predictive models. Training data is accompanied by a ground truth value that is the thing we are trying to predict. The challenge is that we also have model test data, and Kaggle has not provided us with the answers for that data. The goal here is to use the training data to fit a mathematical model, then successfully predict earthquakes in the test set where we do not know the actual failure or quake times. Only submitting predictions to Kaggle will give us a score that tells us how well we did. Let's take a look at the chart and the training data. First of all, the data is huge. There are over 629 million acoustic signal data points. The orange line is the acoustic signal. As you can see, it looks quite noisy. The blue lines ramp down to near zero time. When they jump up, that is where an earthquake occurs, and the blue line switches to the next quake. Here is something that is going to make this a tough project. Not only is the signal noisy, there are only 16 earthquakes to work with. That makes for a tough regression problem where we don't have many actual earthquakes. We'd love to have 100 times as many, but then the data would go beyond gigantic and hard to process. And all competitors have the same challenge on Kaggle, so we forge ahead in our exploration. It might seem from looking at the chart that this is potentially an easy problem, because there is a very large signal spike just before each earthquake. Just find the spike and you know the quake time. Except, as we will see later, there is a big problem. The test signals are so short that the big spike isn't in very many test signals. Worse, on some uncommon signals, there is a fairly big spike that happens without a quake. So, for the most part, we will need to make our predictions without counting on the spike information. When we examine the test data, we see part of the problem. The test data samples are only 150,000 samples long. While this sounds like a lot, it is actually very short compared to the time between quakes, only 0.038 seconds as compared to around 10 seconds between quakes. This is why we cannot count on that big signal spike we noted previously. It is only present in 0.38% of signals. More than 99% of the time, we need to work without the spike. We have no time to failure information for the test data. We need to predict the test signals as best we can and then submit the predictions to Kaggle for scoring. I can only show a few samples here on the slide to compare test and training data. Both are noisy, and short spikes in amplitude are common. It is hard to tell from the small sample shown below how similar or different test and training signals may be. A look at more signals in my exploratory data analysis did appear to show that training and test signals are probably similar in character. And since we can only train on the training data, we are pushed into accepting them as similar. Lots of great scripts have been published by the community on Kaggle. I want to focus on two particularly interesting scripts that were available when this project started. The first is a feature generation script by Andrew Lukayenko. The 629 million sample acoustic signal is sliced into 4,194 evenly spaced subsignals that are 150,000 samples long. For features, this script extracts 154 statistical features from the 4,194 signals. That is a lot of ideas for potentially meaning statistics derived from just one time signal. I used the Lukayenko script as my basis for feature generation, adding digital filters to get to around 900 features and looking at the Fourier transform in a different way. The second script is by Gabriel Preda and provided an introduction to modeling. Gabriel showed great progress with models such as light gradient boosting, and because I was working with so many features, I modified parameters for these models in directions that would help reduce the overfitting that challenged my approaches to the problem. The sliced bread models, where 4,194 test-sized signals are extracted from the training data, had been well explored on Kaggle's published kernels. Partly to do something new, I chose to obtain 24,000 test signals from the data. The way that this was done allowed for several model cross-validation strategies, as we will see. Another change that was made was to look at the Fourier transform of the signal in a different manner. For those of you unfamiliar with this, the Fourier transform essentially extracts the frequencies, or musical notes, from a sound signal. Instead of looking at the real and imaginary, hard math, parts of the Fourier transform, I chose to look at the more traditional amplitude, loudness, and phase, or delay, outputs that can be obtained from combining the real and imaginary numbers. More hard math. Exploratory analysis had indicated that the loudness components probably had significant meaning, but the signal delay or phase part appeared less useful and was mostly noise. As a consequence, I made up more statistics on the loudness part of the signal. Because 4194 models were so well explored on the Kaggle script section, I decided to strike out in a different direction. Instead of slicing the long acoustic training signal like a loaf of bread, random sampling was employed in order to obtain 24,000 rows of data. Because this would cause the Python feature generation scripts to run for a very long time, the data was split 6 ways and parallel processing employed on the 6 splits so that the data could be worked on faster by the Python script. This also has another benefit. It allows stratification of the random sampling so that the random samples are spread more or less evenly across the signal. And, as I realized later in the project, it also allows for multiple cross-validation strategies. We can see this in the picture, where I show the 6 big slices and the extraction of one 150,000 sample slice. Actually, 4,000 training signals are taken from each of the 6 slices. Filtering the data is mathematically complex, so let's make it more accessible. We have one long acoustic signal, or song, that is the training data. We slice it into shorter songs that match the test data and extract lots of statistics, 900, from each song, partly dividing the songs up into groups of its equivalent musical notes. The Fourier transform, musical notes in a sense, is shown for one signal below. I made a lot of these plots, but we will use one to show the direction here. If you look at the plot, it shows all of the peaks are below the 20,000th frequency line. Above that, our acoustic signal appears to be just noise. Part of how I went from Lukayenko's 154 features to 900 features was to divide up the acoustic signal using digital filters. The filters split the signal, taking the tubas, trumpets, and flutes and separating them. This provided more finely divided data for the machine learning prediction algorithms to work with. After exploration, we get to modeling. This is a regression problem. It will probably come as no surprise to machine learning practitioners that advanced decision tree methods outperformed neural networks and also older, somewhat obsolete learning methods such as support vector machines. I concentrated on LightGBM and XGBoost, two modern gradient-boosted decision tree algorithms. Both gave excellent and very similar results on the Kaggle public leaderboard, individually in the top 5% or so, and better with ensembling. But preparation remains king. These models were improved by two insights late in the project. First, because of the way I sliced the data, it was possible to not only take random samples for cross-validation, but also to perform a cross-validation based on the 6 big splits of the original data. It turns out that both cross-validation methods performed well. The original random sampling did slightly better, but using 6 slices provided some diverse models that might at some point help a stack or average of models, and theoretically, using 6 stratified folds avoids leakage where the test signals overlap. Also, 900 is a lot of features, and some are bound to be useless. Pearson's correlation was added. This gives a p-value for feature significance. Using the traditional statistician's p-value, that anything below 0.05 represents significance, added a small boost to model scores on Kaggle by eliminating some less valued features that had p-values above 0.05. My final result model is an average of my 2 best models, one XGBoost and one LightGBM, plus one other model. In the Kaggle tradition of using other people's work to improve one's own, a genetic programming model by a Kaggle user named Skerpus was also added in and averaged with my results. This model is very different than my own, so it should help stabilize the leaderboard result, even though the Skerpus model at the time I submitted it scored slightly lower than my best models. The final results of the model submission to Kaggle have been really great. The model being shown here scored 1.392 on the Kaggle public leaderboard. This is good for the top 1% out of more than 3,200 entrants at the time of submission. Considering that this competition offers cash prizes and thus attracts the best data scientists from around the world, I am very happy with the current Kaggle placing and the project outcome. As this is an ongoing competition, the leader score will fall over time unless I make new breakthroughs. And the final private leaderboard will undoubtedly be different. Thank you for watching my presentation on predicting earthquakes for the Kaggle competition and my master's degree project. As an end note, here are some important references relevant to this presentation.